This is Generalized Linear Models with examples in R, Chapter 3, question 3.27. Okay, so we have 13 American footballers punted a football and had their leg strengths measured. Again, this is in a data set called punting, and so we're going to do some things with this. Okay, so let's first look at what the data looks like. Okay, so we have three variables. We have left, which is the strength of the left leg, right, which is the strength of the right leg, and then punt, which is how far they could punt, presumably with their dominant leg. Okay, so they must have tested both left and right leg strengths, however they tested that, but then had them punt with just, however they were comfortable punting. So the first thing that we're supposed to do is to plot the punting distance against leg strength. Okay, so I'm going to use the pairs command here so that we can see all sorts of stuff. So the first thing that grabs your attention is that everything is positively correlated, which makes a lot of sense. A strong left leg probably means a strong right leg, and a strong punting leg, whether left or right, probably means further punts generally. Okay. So if we want to see leg or punt against leg strength, well then we would just, so here we have punt, and so if I want to see punt as the y-axis and left leg as the x-axis, then it would be this plot in the bottom left, and then for right leg as the x-axis and punt as the y-axis, then it would be this plot right here. Okay. All right. So now, in the next part, we need to show that collinearity is likely a problem. Okay. So, well, there's a few things that we can do here. One is we can just observe these very strong positive correlations, and with quite a bit of success, predict that collinearity is going to be a problem. So that's one thing we could do. The other thing that we could do is to run a regression punt against both leg strengths, and we might expect then that the estimates are going to be highly uncertain when we do that. And so if we do that, we see that at least for left leg, there is a fairly, like the relative size of the estimate to the standard error here is, standard error is quite, it's larger than the estimate. But so in other words, it seems like there is quite a bit of uncertainty for the left leg, but the right leg, it's not as clear. Okay, and so this kind of this is maybe just a little bit ambiguous as to whether or not collinearity is taking place. And so the question asks whether or not collinearity is likely to be a problem. I think that it's likely based on the plot and as well as the estimate for left leg, but the estimate for the right leg makes it just a little bit ambiguous. So what we will do is try to definitively show, not likely show, but definitively show whether or not there is collinearity taking place. And so to do this, we need to install the car package and load it. And then we will just use the VIF command here. Okay, so when we do that, we see that the variance inflation factors, again, if you're unfamiliar with that, you should check out the few videos preceding this or read it in the book. Okay, but I won't go into it here. But we see that the VIF is reasonably high for both of these. They both exceed 5, and usually over 5, we start to believe that variance inflation factor is, suggesting collinearity. Okay, and so the obvious solution here. So what's going on? Well, understandably, the information that is encoded in the left leg variable and in the right leg variable are duplicating one another to a large extent. Okay. That's what collinearity is. And so the obvious solution is to just regress punt on either left leg strength or right leg strength. And so here I'm doing both. And so that's what we'll do here. And we're also asked to kind of give a diagnostic analysis of it. So we run this. Okay, so this is for left leg. This is diagnostic plot for left leg. And we can see that there's, maybe some fitting problems here, like the residuals seem to be, not perfectly neutral. So, as we go right on the x-axis for punt, we see that the residuals are, kind of, following kind of a parabolic shape. So that suggests that there's maybe some fitting problems here. We also see that in the extremes for the QQ plot that, we're starting to fall off this, the QQ line. And in the residuals versus leverage plot, we see that there's probably at least, one reasonably large outlier. And so there could be a few things going on here. One is 7 could be a mistake. And so we'll see what it looks like if we omit it here in a second. But it could also be that, when you're punting a football, there's a few things that are important here. One is strength, and that's what's being captured here. But the other is, technique, and maybe not only strength, but power. So generally strength is, kind of how much force you can apply to an object. But power is how quickly you can apply that force. And really power is the thing that's important, I would imagine, in punting. And so you expect strength and power to kind of correspond to one another, but not perfectly, right? There's going to be people that can generate less maximal force, but can do it very, very quickly and therefore exert more force to the football as they're punting it, okay? And so as you get into, so it could be that, this shape right here in the residuals versus fitted is as you move up and up and up into higher punting values, the thing that is taking people to higher and higher levels is not increased strength, but either increased technique or increased power, which would not necessarily be captured in, the strength measurement. So there's a lot of different explanations here. So now if we look for the just regressing on the right leg, we see similar things. Okay, so we see another kind of, parabolic shape to the residuals versus fitted. We see some guys falling off of the QQ line, and so on. So both of them are kind of having some trouble fitting here. Okay. So like I said, we're going to come back and do the omit, kind of observation 7, because it may be posing a problem, at least in the left leg regression. Maybe not in the right leg, but we'll just see what happens. Okay. But let's look at the summary outputs of both of these things. So right here is for left leg strength. This is for right leg strength, and you're seeing pretty similar inferences, although maybe not similar magnitudes, for the effect of leg strength, whether left or right. Namely, as strength goes up, so does punting ability. Okay, so there's that. Okay, this also makes me wonder. I wonder which leg is better to regress on, or is either leg better to regress on, left or right? Now, we might think right leg, because I don't know this, but I assume probably most people are right-legged, and so you would want the right leg. It seems like maybe the right leg is a better indicator of punting ability, but punting also requires, so if you are right-legged, you're kicking with your right leg, your left leg is also really important, right? Because you have to run up to the ball, I think. Well, I guess that's a kickoff. Depends on what they mean by punt here, but that left leg at the very least is imparting stability. It has to plant in a way that can support the dynamic the dynamic kicking of the other leg. So the other leg is also important. But here, we could compare the two models with AIC, okay, and we see that right leg, might be doing a little bit better than the left leg as the regressor. Okay, so now let me go back through and run these models without observation 7. Okay, So we have just the same setup here, but I'm omitting observation 7 from all of them. Okay, and we'll look at that. But let me say one more thing before we do this. Okay, so we have the option of regressing on either left leg or right leg, and there's been a few things that might make us want to use right leg. One is just the assumption that probably most people are right-legged, and probably the right leg is more important than the left leg in punting ability. Okay. The second one is that this is not a knockdown argument, but that the p-value is far more compelling for right leg than left leg. Okay, so that's kind of interesting to note. And also the AIC value for right leg is better than left leg. And now the final piece here is that we see that for the left leg, you know, if we're concerned about this outlier number 7, well, there is not an outlier for right leg. It's only in the left leg. And so me omitting observation 7 here is a little bit artificial. But we're going to do it nonetheless just because I'm curious about I'm just curious to see what happens. Okay, but all of those are maybe arguments to use right leg instead of left leg. Okay, so having said all that, let's go down here. So we'll just repeat this without observation 7. And so first let's look at the fit for the left leg. I can't see that there's really much improvement by way of fitting for the left leg, and also not for right leg. You know, a lot of the same problems are taking place here. Okay, we can look at the summary values, and again we get, you know, basically the same inferences in both cases. Okay, leg strength is important, so there's that. Okay, and then if we run the AIC, we again get that the right leg is doing better. Note that we could not compare AIC values for these two models with the full data set models. Why? Because AIC needs to assume that the models are ran on the same data. And, you know, in the second slew of models, we omitted one of the observations, so it's not the same data. Okay, we will call that good.